Okay, so let's think of a solenoid. Well, what is a solenoid? It is a special kind of winding a wire, like in the shape of a cylinder, but the winding is in the shape of a helix. So, a solenoid is a type of electromagnet because the aim of this structure, a simple structure that just formed by winding the wire around some kind of cylinder in the shape of this helix. The purpose is to generate a controlled magnetic field through, the coil. This is called the coil. It's tightly, in fact, it's tightly packed into helix. Well, we see that it's kind of loose, but in fact, in reality, these are very tight. So the coil can be arranged, to produce, as I said, a uniform magnetic field in the volume, inside the volume, when electric current is just passed through this. So this is the picture that it's showing the exterior and the interior region of the solenoid. And because of this geometry, we can think of that this winding in the shape of helix is going to produce these magnetic field lines inside the solenoid. And when you draw this tightly winding of the wire, you will see that almost you will produce a uniform magnetic field inside the region, inside the volume of the solenoid, and it's going to be very, very small or very weak magnetic field outside. So our aim is again to calculate the magnetic field strength, this uniform magnetic field strength inside the solenoid by using Ampere's law. Via the application of the Ampere's law, first of all, we have to pick up a closed loop. For choosing the closed loop, you have to be clever, so that you can take the integral in a simple way by just assuming that the magnetic field is going to be uniform inside the region and it's zero outside. By choosing our loop to be a rectangle like this, it's very easy to calculate this closed path integral. Well, since every side of the rectangle is a straight line, for example, for numbering these sides as 1, 2, 3, and 4, for the portion that stays inside the solenoid, it is directed the parallel straight line parallel to the axis of the solenoid. We have this constant uniform magnetic field along the way. It's very easy to calculate this integral at this portion. It's going to be just b times L, right? If you take the size of this longitudinal direction as the L, this integral is going to be just b times L. And the other sides will not contribute anything to the integral, because one thing is that if you go in this direction but the magnetic field in this direction, b dot ds is going to be 0 inside, and outside, since there is no magnetic field, it's going to be again 0, and this side there is no magnetic field, it's going to be 0, and again for the fourth side it's going to be 0 contribution. So all contribution comes from only this side, and it's nothing but b times L. And if you apply the Ampere's law, this loop will contain 1, 2, 3, n number of currents that flows through the plane of this rectangle, as it's seen very clearly over here. So since we don't know this number, we just type capital N times I, and to find the magnetic field, just solve this equation equality for B. When you solve it, you get the mu 0 multiplied by the number of lines, number of currents or wires that once crossing this rectangular region, and divided by the length L of the solenoid and multiplied by I. But if you look at it very carefully, this number n divided by the length is nothing but the density of these currents along the direction of the solenoid, right? So if you know, for example, let's say for the 10 centimeters of that, you have, let's say, 100 of winding. In that case, the density is going to be 100 divided by 10, which is 10, but this density is going to be same everywhere. So you can use the same equation for everywhere, every part of the solenoid to find that the magnetic field strength is just mu0 multiplied by the number density of the wires in the axis direction of the solenoid multiplied by the current I that passes through every of the wire for the solenoid. Well, by saying that every of the wire, in fact, we have only one wire, but we have many turns, and it's just the number of turns per length in the direction of the axis of the solenoid. Okay, so that's it. I mean, it's very easy to find the magnetic field by using the Ampere's law for a solenoid inside the solenoid, which is assumed to be a uniform magnetic field in a certain direction, in the direction of this axis of the cylinder. Depending on the direction of the wire, it is either up or down. If you change the direction of the current, of course, you can change the direction of the magnetic field. Also, if you change the strength of the current, you can change the strength of the magnetic fields. They're linearly proportional to each other. Okay, so